Okay, so we're going to start today just getting some terms straight. Properties, states, and processes. Intensive versus extensive properties. We'll talk about temperature, and then spend some time talking about pressure. And then we'll get into the first law of thermodynamics today. Okay, so first, properties, states, and processes. A property is a measurement that represents let's say a chosen body or a chosen system is better at an instant. Examples of properties are temperature, pressure, volume. You don't need to know anything about the history of the system to measure those things. All you have to know is what's going on at that instant. The combination of all properties is called a state. So this is all the properties at an instant. So, excuse me, the air in this room right now is in a certain state. It has any measurement you want to take. It has all that stuff, a temperature, a pressure, it has volume, and all that stuff together describes the state of the air in the room. Processes are transitions a process is a transition between two states. These are where the laws of thermodynamics are going to apply. In a state, we're not going to use the laws of thermodynamics, but we will use equations of state. And equations of state are things that relate, properties in a state. So if you know some properties, you can often calculate other ones. The ideal gas law is one of those. Thermal expansion equations are included in those. Tables of thermodynamic properties, we'll use those quite a bit. Okay, so for example, let's say that a gas initially has a pressure of 2.0 times 10 to the 5th pascals, a temperature of 350 Kelvin, and a volume of 0.6 cubic meters. And then it's compressed to a pressure of 3.0 times 10 to the 5th pascals, temperature of 400 K, and a volume of 0.3 cubic meters. What are the properties? States and processes. Well, there's two states in this problem description. The first one is what's going on at instant 1. The second one is what's going on at instant 2. So state 1 you can think of as with the pressure of 2 times 10 to the 5th pascals, the temperature of 350 Kelvin, the volume of 0.6 cubic meters. These things are all properties at state 1. State 2 is made up of the properties 3 times 10 to the 5th pascals, 400 Kelvin, and 0.3 cubic meters. Again, those things are the properties. And the process is as this thing goes from state 1 to state 2. So the equations that we'll see in this class, they can be either equations of state, and equations of state relate properties at a single state. The example that we'll use the most is the ideal gas law, and we'll write that in this class. Well, in its extensive form, we'll write it as P times capital V is equal to N times R bar times temperature. Okay, the ideal gas law doesn't have anything to do with time elapsing. It just has to do with what's happening at a single instant. And the second type of equation will relate to processes. And these will be the laws of thermodynamics. And a few other things too. There are two types of processes. Extensive and intensive. So first, let me talk about extensive properties. Extensive properties are only defined once you choose an amount of material. And if you break up material into pieces, so let's say that this is some amount of material, and say that we just break it up into, what am I going to call these? I'll call this region 1, region 2, region 3, region 4, okay? Then for an extensive property, I'll call that capital P. It's just like an arbitrary, any old extensive property. The property of the whole thing is equal to the property of region 1 plus the property of region 2 plus the property of region 3 plus the property for region 4. Can you think of any properties of materials that satisfy that? Mass, yeah, exactly. Mass is probably the best example. So you can't talk about the mass without choosing an amount of material to deal with. So examples are the mass, and we'll denote that with a lowercase m. This is really the only that I can think of, the only extensive property that's going to be denoted with a lowercase. Usually intensive properties are going to be lowercase and extensive properties are going to be capital. But mass is extensive. volume is a capital V. Area, well, we're not really going to use area much. We'll be doing stuff in 3D because we'll mostly be dealing with gases. So these are almost always represented by capital variables. Capital letters. What we're going to use more often is intensive properties. These are properties that are measured per unit, and what the unit is that you measure, that can be different. What's an example of a property that, like, say, air or liquid can have that doesn't meet this requirement of extensive properties? Temperature, yep. So if you take the temperature of every region of this room, you don't add them up to get the temperature of the room, you know. Examples are temperature, and we'll denote that with a capital T. And just like mass was the only extensive property we're going to use a lowercase letter to represent, temperature is the only, or at least one of the only, intensive properties that we're going to use a capital for. Normally, we're going to use lowercase to represent intensive properties. Then there's density. We'll denote that with a lowercase rho. Density is mass divided by volume. So it's like the mass per unit of volume. In SI units, that's going to be in kilograms per meters cubed. Next, specific volume. We're going to denote that with a lowercase v. And that's volume per mass. That has SI units of cubic meters per kilogram. And I put these two together because this is an important thing to notice. These are both variables that are important in calculations. And if you know one, you know the other. They're just the reciprocals of each other. Okay, so notice that this is, let me write it as specific volume is equal to the reciprocal of the density. Okay, so if you're ever working on a problem and you're given density and you don't know how that would come into the problem, be expecting for specific volume to come into the problem and recognize that if you know the density, you know the specific volume. Okay. Another one is pressure. we're going to use lowercase p for that. That is equal to the force per area. And we're going to talk a little bit about what you know if you know the pressure later on today. That has SI units of newtons per meter squared, and that's pascals. Temperature, I didn't give the units. SI units for temperature are Kelvin. Intensive properties are almost always represented by lowercase letters. One thing to look for is intensive properties that have an overbar over them. So if you see an intensive property with a bar over it, that means per mole of material. So for example, lowercase v over bar is volume per mole. In chemistry, I don't think you probably use the overbar for the universal gas constant, but here we're going to, because the gas constant without a bar is going to mean something else, and this is the one that's measured per mole. So R bar is, joules per mole times Kelvin. And you can think of that as joules per Kelvin per mole. And that's, so this is an intensive property measured per mole.
Wait, quick question. So
yeah.
R without the bar, would that be the same thing as Boltzmann's constant? That's usually represented by K?
No, it's something that you probably didn't use before. It's a gas-specific gas constant. Okay. So that you can still use the universal. You can use the gas law, the ideal gas law, with the R without an overbar, but you need to use a constant that's specific to the gas that you're using.
Okay, yeah, that's right. With Boltzmann's constant, you use number of particles as opposed to lowercase n, which is the number of particles per mole. I forgot, or number of moles. That's what lowercase n is.
Yeah. Great. Okay, any questions about that? Okay, let's talk a little bit about temperature. I don't think this will be really new to people for the most part, but make sure we're all on the same page. So temperature is a weird unit because the temperature scales, the common temperature scales, were defined before people understood what the true zero was. And so they have zeros in different places. There's no other kinds of units that have that. That's what causes all the problems. It would be very confusing to use mass scales too if something that weighed 20 kilograms was called zero mass in one, but most things, what zero has a pretty obvious meaning. With temperatures, zero didn't always have an obvious meaning. So temperature can be tricky because different units have different zeros. Or let's say 0.0, yeah. And what this means is that you have to be very clear to yourself about whether you're talking about a difference in temperatures or instantaneous temperatures as a property. So you have to always be clear. Are you dealing with a temperature difference or an instantaneous temperature? Because unit conversions are different depending on which one of those you're dealing with. You approach them differently. So you do temperature conversions differently for each of those cases. There are 4 temperature scales that you'll probably ever use, I suppose. So the 4 common temperature scales are Celsius, Fahrenheit, and then the 2 temperature scales that are basically these, but have been adjusted so that the zeros are absolute zero. So Kelvin, that's the one we're going to use the most because that's the SI temperature, but that's the same thing as Celsius, but the zero is absolute zero. And then Fahrenheit with the zero at absolute zero is called Rankine. So these two have the property that zero means absolute zero. Fahrenheit and Celsius don't have that. Okay, so because of this funny thing with the zeros being different, instantaneous conversion of Fahrenheit to Celsius, say, you use one approach. Differences in temperature from Fahrenheit to Celsius, you use a different approach. And like, for example, if you say the temperature right now at this instant is 5 degrees Celsius, that means something very different than the temperature right now is 5 degrees Kelvin, okay? But if you say the temperature has risen 5 degrees Celsius, that means the same thing as the temperature has risen 5 degrees Kelvin. Okay, that's the difference between instantaneous and change. Okay. So first I'll talk about just instantaneous temperatures, so unit conversions. For instantaneous temperatures. The temperature in Fahrenheit is the temperature Rankine minus 459.67. Or in other words, the zero Rankine is equal to negative 459.67 degrees Fahrenheit. Temperature in Fahrenheit is equal to 9/5 of the temperature Celsius plus 32 degrees. And temperature in Celsius is the temperature Kelvin minus 273.15. Or in other words, absolute zero is negative 273.15 degrees Celsius. Okay, so with those three, you can get around from any unit to any other unit of temperature. Okay, so now how about conversions for changes in temperature? So first, a change in Fahrenheit temperature is the same thing as a change in the Rankine temperature. A change in the Fahrenheit temperature is 9/5 of the change in the Celsius temperature. And it's also, well, I'll do that in a second. And a change in the temperature in Celsius is the same as a change in the temperature in Kelvin. Okay, so when you see temperatures, you need to know whether you're talking about a change or temperature as a property. Any questions about that? All right, now let's talk about the definition of pressure. That's going to be a really important thing for us. Pressure is mainly applicable to fluids. Sometimes you see pressure in discussions of solids. And by fluids, I mean gases and liquids. So this is mainly applicable to fluids, liquids, and gases. And the pressure is the force per area that the fluid applies to, that a fluid applies perpendicularly to a surface. Okay, so even though pressure isn't a vector, it's just a number, a value. You can get vector information out of it if you know the orientation of a surface that the pressure is being applied to. So for example, if you have a vessel like this, and let's say you have a flat plate inside, okay? And let's say that the pressure inside is P. Then that gas of pressure P is applying force vectors in this direction to the vessel. At every location, it's perpendicular to the surface. And on this plate on the inside, it's applying force vectors in these directions. Everything's perpendicular to the surface. We, in everyday speech, talk about suction, but really there's no such thing as suction. There's just fighting pressures on the two sides of things. So like things like, if you imagine like a plastic soda bottle, you know, when it's empty, you can suck in and it feels, you have this feeling like you're sucking in the sides. What you're really doing is you're decreasing the pressure of the gas inside the bottle and not decreasing the gas on the outside of the pressure of the gas on the outside of the bottle. And so you're making it so that the pressure, the atmospheric pressure on the outside of the bottle just wins this battle of pressures to deform this bottle. Okay, there's no such thing as suction. There's only pressures fighting against each other. Okay. And that's because of the mechanism that pressure comes from in a fluid. Pressure is really just molecules bouncing off of surfaces. You know, the air in this room is just a lot of molecules just bouncing around. And a lot of them are, so if you're measuring the pressure on the door, a lot of these molecules at any instant are hitting that door and it's pushing the door out. Those molecules aren't grabbing the door and pulling in. That's why there's no such thing as suction. Okay. If a fluid, and that's a liquid or a gas, is continuous and at rest. So those are the two requirements. Then the pressure at the lower point, at a lower point in that fluid, minus the pressure at a higher point in that fluid is equal to the density of the fluid times g, the acceleration of gravity, times h. This is going to be an important thing for calculating pressures in fluids at rest. So let me define all these things. This is the pressure at the lower point. This is the pressure at the higher point. Rho is the density of the fluid. G is the acceleration of gravity. So this could be true on the moon too. You just have a different acceleration of gravity there. And then h is the height difference between the higher and lower points. So you could use this to figure out the pressure at the bottom of a swimming pool, or you can use this to figure out the pressure in a gas. Let me draw a picture that sort of illustrates this, the meanings of these things. So if you have a continuous fluid at rest, then this is your P lower. This is your P higher. And this is your H. Okay, how important are the two requirements of continuous and at rest? I mean, they're everything. Okay, this doesn't make any sense if you don't keep those in mind. So why doesn't this hold for the first one? So imagine you pump up an inner tube tire. Okay, and now you have this point and this point. Okay, so that's inner tube tire inner tube. Well, these 2 points are at the same height, but the pressure inside the tube is much higher than the atmospheric pressure. So why doesn't that rule hold here? Because that gas isn't continuous. The inner tube is separating the high pressure gas from the low pressure gas. Okay. And on the other hand, let's say you have gas moving through a tube that has a restriction okay? It's going this way. What you would get is a low pressure here, a high pressure here, and then a low pressure again here, okay? They're all at the same height, but that's because this gas is not at rest. Let me write that in here too. So the idea of this inner tube one is that there's a high pressure inside the tube and a low pressure outside the tube. It's because they don't meet those requirements for this equation to hold. Okay, so using this law, does this law have a name? I feel like it does. I don't have it written down though. But we're going to use this for the two main ways to measure pressure. The first one is a manometer. And you use this for measuring the pressure inside an enclosure. Yep. I don't think that's right. This is an hour 20 class. What time do we start? Okay. We started at 12, right? Okay. Statics is 50 minutes. This is an hour 20. Yeah.
Yeah, also, real quick for case 2, is that Bernoulli's law? I think that relates.
Yeah, that's right. That is correct. Yep. Okay, so a manometer measures the pressure inside an enclosure. And so if this is your enclosure and this is the gas that you're trying to measure the pressure for, and you have this open tube and the top is open, and you have a fluid inside here, and that fluid is chosen based on its density for whatever purpose you're using this for. Okay, since that tube's open at the top, the pressure at the top is atmospheric. This distance is h. The red is a liquid with density rho. And we're trying to figure out the pressure P of this gas in this enclosure. So to calculate that, we know that the lower pressure, the pressure at the lower point, P, minus the atmospheric pressure, is equal to the density of the liquid times G times that difference in height. To measure atmospheric pressure, the other tool for measuring pressure is a barometer. And this system looks like this. You have a closed column where up at the top it's evacuated, so the only pressure is the fluid pressure coming from the liquid. And you have a tray here that's open to the atmosphere. You have a liquid inside, sitting in the tray and keeping air from going directly into the column. So this is your liquid with density rho. Up here, this is evacuated, so you do have a vapor pressure there, but it's very small, so you can treat this basically as zero pressure. And at the surface of the liquid in the tray, you have atmospheric pressure. Okay. Your H is this. And so our equation relating these pressures says that the pressure at the lower location, that's the atmospheric pressure at the tray, minus the pressure at the higher location of the liquid. That's up here, but we said that pressure is zero, is equal to the density of the liquid times acceleration of gravity times h.
Yeah, you said it's an evacuated chamber at the top?
Yeah.
Okay.
Yep.
Yeah, and vapor pressure, that just refers to the vapors evaporating and that balance?
Yes,
okay.
That's right. Yep, exactly. Okay, so let's just do a couple of quick examples with these. It's a pretty simple algebraic equation. So let's say that first, with a manometer, let's say that the liquid we're using is mercury. Oh no, actually, for this one, let's say this is water. So anyone remember the density of water? Yeah, it's 1 gram per centimeter cubed, or 1,000 in SI units, 1,000 kilograms per cubic meter. And let's say that we measure this distance h to be 0.8 meters. So what's the pressure in the bulb? Well, the pressure that we're trying to find is that lower pressure. We'll call that P.
So that's equal to the atmosphere plus rho GH.
That's right. Yep. So, and the standard atmospheric pressure, I didn't give one here, so we're just going to assume that it's at its standard value. So 1.01 times 10 to the fifth pascals. Is equal to the density. We're doing everything in SI units, so I'll just leave the units off. 1,000 times the acceleration of gravity, 9.81, times the height difference, 0.8. And you get a value of 1.088 times 10 to the fifth pascals. If you carried through the units, it would all work out, but let's not do that. Any questions about that?
So you said value of 1.088 e to the power 10 to the fifth, is that P minus the atmospheric pressure is equal to that?
No, thank you. That is incorrect. That is P.
Okay.
Yes, that's a really important point. I just wrote that wrong. So P is equal to 1.088 times 10 to the fifth pascals. Okay. That's the standard atmospheric pressure. Yep. So it varies a little bit day to day and stuff, but that's always a good, if you're not given a value, that's a good value to plug in if you need atmospheric pressure. Let's do one with a barometer. So we're going to assume that the pressure up here is 0. Here, so this time we're trying to measure this atmospheric pressure. So that's what we want to figure out, the pressure at the surface of that liquid. And let's say that the distance on this day where we're taking the measurement is 0.55 meters. And this time the liquid we're using is mercury. So the density of mercury, that's just something you can Google. And it's 13,690 kilograms per meters cubed. Anybody remember what the density of steel is? How does mercury compare to steel in density in mass per? So say like if you have a cubic meter of steel and a cubic meter of mercury, which one's heavier?
Isn't mercury heavier?
Yeah, about twice as much. Steel is about 7,000. Water is 1,000.
Yeah.
So I don't know. That's a little intuition for you.
A quick question. So was mercury just used because it's a fluid that has a low vapor pressure?
I would guess that I don't know that that's something special about it. I would guess that the reason it's used, like in, I mean, in this case, you're using it because it has a high density. I think, and it's a liquid with a
higher density, so you'll have bigger spaces in your tick marks, like on your meter. Would that be the case?
You would have lower distances.
Would be lower distance?
Yeah. So if you wanted to do this with water, you need to have a thing that was really, really high, you know?
Okay.
Yeah. With thermometers, I think mercury is used because it has the right, so in this case, it's the density that's the right value. In a thermometer, I think it's the coefficient of thermal expansion that matters. You know, if you use something with too low or too big of a thermal expansion, your thermometer has to be either tiny or.
Yeah, that makes sense now.
Okay, so we have all the values, and we want to know what's the atmospheric pressure. So our atmospheric pressure minus the pressure at the top of this column, which we're going to treat as 0, is equal to, in SI units, 13,690 times 9.81 times 0.55, and you get an atmospheric pressure of 73,864 pascals. Atmospheric pressure, standard atmospheric pressure at sea level is 101,000 pascals. So this is really low. Maybe this is a place at pretty high altitude or something. Any questions about that? Okay, let's go on to the first law of thermodynamics. And remember, that's just conservation of energy. And so I want to relate the way we're talking about it to the way you talked about it in Physics 1. This is conservation of energy. So in Physics 1, you use conservation of mechanical energy and it looked something like this. The work that you apply to an object is equal to the change in energy of the object. Where the energy is equal to the kinetic energy plus the potential energy. And potential energy is just the negative work that's done by a conservative force. So you could just write this as, you could just have the total mechanical energy, total change in mechanical energy be the change in kinetic energy and just have everything included in the work and not deal with potential at all. And then with this definition, work is all work done on the chosen object by non-conservative forces. What are conservative forces? Anyone remember?
That'd be forces that are, what do you want to call it, not path dependent.
That's true. That is totally right. I like to think of it as just forces where if you know an object's location, that's enough information to know what the force is. You know, so gravitational forces, forces applied by springs, electric fields, magnetic fields. These are all things where if you know the location of your object, that's enough to calculate the force applied. And why do we define conservative and non-conservative forces? In a way, everything would be a lot simpler if we had ignored that completely and just calculated the work as the work done by every force. But the reason is that potential energy is a very simple way to calculate the work done by a force in the case where there is potential energy, and not everything has potential energy. You need to be conservative in order for potential energy to be defined. Okay? So we'd love for there to be potential energy for everything because it's simple to calculate, but there isn't, so we use it for the things where it is defined. That's why.
Potential energy from a friction force?
There's no such thing as that because a potential energy needs to be calculable by the location of the object.
Yep.
And you can't do that with friction. Yep, exactly. Okay, so it's the same idea in this class. But there's two changes. The first one is now we're going to include thermal energy. And that shows up in two ways. First, we're going to use a change in an object or a system's energy due to a difference in temperatures. That's called heat. So the heat Q is a change in system energy due to a temperature difference. And in physics 1, you didn't have anything like that. That's why you called it conservation of mechanical energy. We're only dealing with mechanical energy, no thermal energy. And the second type of thermal energy that we're going to deal with is called an object's internal energy. And we will call that capital U. And it's capital because internal energy is a property of the system, and it's an extensive property. If half of it has this much energy and half has this much energy, the total thing has, you add them together. Okay. And the second change is the one that I brought up last time about the sign convention. So there's this new sign convention that you always have to be aware of. And it comes from, remember, the power cycle. So remember, in the power cycle, you can think of a cylinder with a piston. And the gas is inside the cylinder. You add gas to the system, and the result is that work is done and removed from the system. So positive Q is heat added to the system. And positive W is work done on the surroundings by the system. Okay, so if you keep those things in mind, other than that, it's still just conservation of energy. And so this equation looks like this. The change in energy of your system is equal to the heat added to the system minus the work done by the system, where E is equal to the kinetic energy of the system plus the potential energy of the system. I'll label all these, plus the internal energy of the system. And the internal energy of the system, you know, like if the temperature rises in something, it's increasing in energy. That's the internal energy. So this is kinetic energy. Capital V is potential energy. And capital U is internal energy. Very often, I suppose probably usually in this class, we'll ignore changes in kinetic and potential energy. The thermal energy is going to be a lot more important. And also, you know, we usually won't have, if you're talking about like a tank that's being heated up to produce energy, you don't usually have changes in height of the tank or changes in speed of the tank. That's what would cause kinetic and potential energy changes. So usually we'll ignore kinetic and potential in this class. One type of work that we're always going to use So one type of work we'll always use is the work done by gas in expansion. This actually holds for liquids too, but they don't expand very much. Gas can expand quite a bit. And that has the form work is equal to the integral from the starting volume to the ending volume of the pressure of the gas dV. When can you compute this integral? The easiest case is if the pressure is held constant. But you can also do it if, so what you need to be able to do it is you need the pressure to be known as a function of the volume. Okay. It's easiest if the pressure is equal to a constant. Okay. You can imagine how to compute that integral, I think, if in the case of a constant pressure. So say that you're going from a volume of 0.1 cubic meters to a volume of 0.3 cubic meters. The gas is expanding. Pressure is atmospheric pressure the whole time. Well, you can pull the pressure outside of the integral, and then you just have that pressure times the difference in the volumes. This is the last thing I'm going to say, and then you're done. So notice that work is always positive if the volume increases. Okay, that's it for today. I will look and see if I think there might be a few problems I can assign. So look on D2L maybe tomorrow morning, and I'll get all that stuff up hopefully by the end of the day today. All right, see you Tuesday, right? Yeah.